How are you?
Good. I'm glad to hear that. Hello everyone. I hope you're all doing well. A lot happened. I guess if I include basically every day since I last saw you as the weekend, then a lot has happened. Too many things in too few days. I think we're going to take a vacation now. Good news, there's one coming up soon. It's going to be a pretty long one, so I'm excited about that. Now, one of those things that happened was Halloween, and I usually like to at least have a little more fun with that when we have a chance to. I actually like to just dress up as someone I can do an impression of and wear my costume to work, but you know, life is weird right now. But I didn't want you guys to miss out on all of the fun, so on that sanitized table right there and scattered so that no one piece has to touch another is some candy that you are all welcome to for as long as it remains. So please help yourselves at any time. There's some fruit and some chocolate-based ones there. So hopefully there's something for everyone. I'm surprised that my church actually went through its Halloween event, but we made a contest out of how everyone building a method to dispense candy from 6 feet away. I dressed as a mad scientist and built a conveyor belt.
Did you win?
I don't really know if and how the voting took place.
Really?
Normally the guests vote, but there was no booth for the guests to stand around and make decisions at this year because we didn't want them to all stand next to each other touching things. So, I don't know, but at least I made the kids laugh. Okay, so, big thing that we have moving forward is the test. This is the test 2 on chapters 5 through 8. It is available to be taken at any point you wish or is convenient for you between today and next Monday. So you have, excuse me, it's called the calendar. So today is Thursday the 5th. The test is available from today through Monday 9th. The reason you can't take it Tuesday is because we're going to talk about it in class on Tuesday. Pardon me. So, the way it works will be similar to last time. You send me word when you're ready to begin. I'll send you the document, and you'll have 5 hours to get me your answers for the 1-hour assignment. That said, since we don't have lab this week, to give people time to study and take the test, I will be in this room during when lab would normally be, 1:30 to 4:30. If you have questions, like if you want to come in and ask study questions or review things. Additionally, if you want to take the test in person, because you just want to have the physical tactile paper, or if you want me to be there close at hand so that you can get answers to your questions faster, that would be a pretty good time for it, because I will be in this room for a decent length of time. You don't have to. Coming today is completely optional, but it's an option if you prefer that way. I also have, this class doesn't have a lecture on Fridays, but I will be in this room for the other class, the other section's lecture on tomorrow. That's also entirely a review day, so odds are a lot of people aren't going to show up. If you wanted to show up then to also take it in person, you can, or if you wanted to show up for study questions. Options abound. You don't have to come and do any of these things. Do what best works for you, and I will work with you on it. So today we can go over any and all information about the test, any questions you guys have, look over the answers to the practice questions. Why does my phone keep going off? And it's a review day. If at any point you feel like you don't need any more review and that you are completely prepared, I will not force you to remain here. As a matter of fact, unless you guys continually have questions or continually find new things to study and work on together, it's entirely likely that we will cover all the information in less than our standard lecture time, again, at which point you So, but while I've got the calendar up, the test is available through Monday. On Tuesday, I'll talk about the grading, the test with you guys as I am in the process of grading it for everyone. We'll spend the rest of that week, maybe a little bit of the week after, talking about a few additional topics, namely electricity and waves. If for no other reason than they are important things to know because you live on Earth where those things exist and shape your life. There won't be a test on those, they'll just be added onto the exam. We'll only be doing that for about a week. Then the rest of this week, 17th through 20th, will be entirely geared towards exam review. Since that's the last week of lecture before exams start, there won't be any new assignments. It'll just be preparation, making sure everyone's comfortable. Exams themselves, I believe the information exists, it's just not in the top of my brain at the moment. Exam days for the entire school are 22nd through 25th. I think this class's 2 exam times are on 22nd and 24th. I'm still finalizing exactly how those are going to work, trying to figure out exactly what I'm allowed to do. But at least at the moment, there will be an online option. But if we also have an in-person option for those who would prefer it, since I'm giving the same exam twice, once for each section on the 22nd and 24th, I don't care which day you show up. I don't care which time you show up for, as long as you eventually take your exam. So that, more details there to follow. You're in the home stretch. This is the very end of it, and you can have Thanksgiving and Christmas and New Year's, and all should hopefully be well. So we're in the home stretch. We're going to end strong. Any questions, comments, concerns from you guys about class stuff as a whole before we get into test review? Again, you all had nice weekends. Hope things are continuing to go well for you. Now, let's see here. Oh no, building in that is down. I hope I can get to my scan copy. Oh no. Don't you just love the internet in this particular building? You have a cinder block which blocks the Wi-Fi.
This really is the worst building for Wi-Fi. Because the football team has study hall in the big auditorium right there. No, in the big auditorium, and it's terrible in there too.
Well, we have, is there one in this room? Occasionally there's little like things attached to the ceiling that kind of look like smoke detectors that are actually Wi-Fi extenders.
Really?
So there should be Wi-Fi in this entire building. It's just a question of where are the extenders and is every spot in the building within reach of one, or does the signal have to pass through a cinder block wall? Okay, so that's on chapters 5 through 8, and as such, get bright space up on the screen. So on our bright space page, we have a test 2, chapters 5 through 8 tab. Tab itself, we have test rules and procedures, followed by the list of topics. I talked about each of those in the pre-recorded video I sent out for you to watch on Tuesday. Also in this tab, again, we have the formula sheet. This is just chapters 5 through 8 on here. These are all the formulas that you will need on the test. Nothing from 1 through 4 will be present. This is just the formulas, and they are labeled by chapter, if that helps you with remembering them. And so that, okay. I am already thirsty to take a quick pause to review my thoughts. So, okay. There is some additional information that one might want when taking this test that isn't on this, namely tables like these, like the specific heat, the thermal conductivity charts. That information is not on this sheet because these tables are on the test next to any question that needs them. So if there's a question that asks about specific heat and it says this material is steel and you need to know the specific heat of steel, the specific heat table will be right next to that question, just so that there's fewer documents for you to keep track of. So any chart you need, any information, constants you need will be on the test, and this is just the formulas you plug them into. You can print this out, mark it up, or just come back here whenever you need any of these. Then we have the practice questions, which I hope you've all been glancing at as a part of your studying. We can talk about these today as good examples, and beneath just the blank document is the answer key. In the email I sent out yesterday, I did confirm that yes, these are bad to read because of the scanner I had to use last night. I have since scanned them on a nice fancy one upstairs, so I have a better copy, which I'm going to and should now upload. A brief glimpse into Well, I'm fiddling around with technology. Do you guys have any questions about any Chapter 5 year content on the test? If not, we can just review things generally for as long as you guys, for as much review as you guys want to say. All right, so this is the new key. Why can't I rotate it? Isn't technology fun? Okay, the key is here, and if you download it, you will be able to rotate it. Just hide it. Okay. We addressed one of them. We do each other today, but the new version is there. It's easier to read when it's right side up. Boy, I feel derailed right now. Thankfully, at least for the moment. I can just put the file open. All right. I know my handwriting is still awful, regardless of the scanner used. So if anything is just not legible, please let me know. If you don't have any specific questions, I would like to go through some of these samples with you guys. I have gotten a few questions about some issues with these. If you have any specific needs while we're going through this, please stop me and let me know. But to at least touch on most of these in brief. The first page of the review document is all concept questions. Very brief sort of concept stuff. Notice, as often as I can, I do try to write a very, very brief description because I'm not grading you on writing an entire thesis statement. I just want the main points that are important for everyone to remember, which is how I try to summarize them in lecture. So, what is thermal energy? We define energy as just a thing that matter possesses that lets it do stuff. When and something specifically has thermal energy, its particles are moving around more, bouncing off of each other. It can be thought of as kinetic energy on an atomic level, because kinetic energy makes mass move, and thermal energy makes the mass of subatomic particles move. Very briefly describe the three methods of heat transfer: conduction, convection, and radiation. Conduction is simply through direct thermal contact, i.e. touching. Convection requires convection currents in a fluid medium. It only works through like water and air. And then there is radiation via light or other electromagnetic radiation. This next part I'm about to say is not necessarily on the test, but it is what we're going to be talking about next week, and I really like it, so if you'll indulge me for a moment. Everything written up here, gamma, X, UV, light, infrared, this is supposed to be the micro symbol, and radio. These are all forms of electromagnetic radiation, which means these are all the different ways that you can radiate energy. All of these, they're basically the same thing. Light and all these others are just the same kind of thing, slightly different flavors though. So they're all chocolate bars, just a question of what, like Hershey's or almonds, etc. And because they're all basically the same thing, they're functionally just traveling energy. When that energy strikes something, it will be absorbed into that object as energy, usually thermal energy. So that is how light warms the earth and everything else. So technically, you in this moment are being irradiated. Because light, among other things, is a form of radiation, so you are being blasted with radiation right now. And you are gaining some warmth from it. But humans also give off radiation. For one, light bounces back off of us. That's how we can see each other. Light bounces off of me, namely orange light at the moment. And that's why you see orange when you look at my shirt. But humans themselves are also radioactive. We also radiate energy out of us because we're warm-blooded. We make our own thermal energy. We give off some radiation in that process. You know, like night vision goggles, infrared goggles, those work because your body is literally giving off infrared radiation right now. You are irradiating at this moment. It doesn't do anything to you. It's harmless. Your body's designed to do that, but it allows you to be seen on those goggles. Similarly, it allows snakes to see you because they have infrared senses. Additionally, besides just giving off infrared, you also give off one gamma ray every single second because the calcium in your bones is naturally a little bit radioactive. So you are literally radioactive. You are giving off gamma rays, just not enough to break the Incredible Hulk. So those are all forms of radiation. We'll get more into that next week. For right now, know that thermal energy can transfer through radiation, and you are doing it right now. Then, temperature conversions. Make sure you can convert from one scale into another, the formulas for which are on your formula sheet. Which temperature unit is the best one to use in most of our formulas? Kelvin. All formulas will work with Kelvin. Some will work with Celsius. None of our formulas will work with Fahrenheit unless the formula is converting Fahrenheit to something else. Additionally, it's not, notice, no degrees Kelvin. It's just Kelvin. I don't know why, it just is. And then, very brief description of the laws of thermodynamics. What I will say about these is, I'm not going to require you to write them in length off the top of your head. What's going to be on the test is I'm going to list various statements, and you need to number them, which one is which. There will be some statements that aren't laws of thermodynamics. There will be like 6 statements. You have to pick which 4 are and give them the correct number. 2 of them will be blank. Just because I get questions about how that one works whenever it comes up. So, first page is concepts. Second page, we're beginning with math now. I've been getting some questions about this one as the weekend gone on and as people were doing it. So, at least talk about it in brief. This particular question is basically just one long conversion. We're just taking information about the human body and the food we eat and using a couple basic multiplication conversions to make a conclusion about how much time one pizza slice fuels the body. So, basically the human body is just you can think of the human body as an organic machine, and rather than plugging in batteries, you just eat food and you get our energy from that. Average human being, this will vary highly depending on who you are, but at least average, a human adult who is awake, sitting upright, and engaged in light activities such as moving your muscles, desk work, basically as long as you're not lying down on your back. And you use about 230 joules of energy, mechanical energy, every single second. That's just the energy drain of being awake, basically. And at least some of that is actually energy used thinking. It's not something that comes up much, but you do burn calories by thinking, because it takes energy. Now, we get our energy from our food, so we begin with the statement of joules per second, and joules per second is the same as watts. Joules per second is watts. So you can think of this as a ratio, joules over seconds, but you can also think of this as the power requirement of a human being. So that 230 can be plugged into a formula for power. Power equals energy over time. Again, like up there, joules per second. We know the energy per pizza slice, it is given in calories, so you need to convert calories to joules. It's going to be a very big number, like a couple million, I think. And so you figure out how many joules are in a single pizza slice, then figure out how long one pizza slice will fuel you. What I did up here is I just set up a conversion. We got calories per slice. This part converts the calories into joules, and this part I'm using the 230 joules per second as another part of the conversion, and I'm just canceling out joules to replace them with seconds. That will leave me with seconds over pizza slices, seconds awake per slice. And you end up with over 5,000 seconds, which is roughly about an hour and a half per pizza slice. So, metrically, one whole Little Caesars pizza should keep you awake and going for a whole day. And then you go to bed. Assuming there's about 8 slices, 8 times 1.5 is about 12 hours awake. Okay, have something else, maybe some grain bread. You can do it like this, sort of as a conversion chain, but you can also just use the power formula because 230 joules per second is the power equal to energy per slice divided by time. Solve for time and get seconds. I've probably got questions about this one because unless you see that connection, it's not obvious what formula to use, and you can get through it without a formula, technically speaking. You can just treat it like a conversion, but this is just, it's simply about energy use, therefore power. Then we have a solid cube of aluminum. Will it float? There is a piece of information I didn't actually say in this question. I didn't list the density of water. I apologize if that number is needed on the test that is mentioned. But in order to find the buoyant force acting on the aluminum cube submerged in water, buoyant force is density times volume times 9.8. Remember that the density in this formula is the density of the fluid, not of the solid object in the fluid. So we don't plug in the density of aluminum, we plug in the density of water, 1,000 kilograms per meter cubed. This piece here, if you look at the formula, it's density times volume. So this is solving for the volume of the cube. It says that it's a cube, and its sides are all 1 meter long. Volume of the cube is just length by width by height. So 1 times 1 times 1, 1 meter cubed. And then last but not least, times 9.8. This is the buoyant force pressing upwards on the cube as it is submerged. Now, there's 2 ways to determine if this particular object will float. The first is the general rule. Something will float if the buoyant force upwards equals the force of gravity downwards. You can solve for the force of gravity, compare it to this. Depending on which one's bigger, it will either float, sink, or shoot up to the surface violently. But the other quicker rule, one that most people are familiar with, is if this is the density of water, you have to be less dense than this in order to float in it. Humans are as dense, maybe less dense than water, which is why we can sort of float just at or beneath the surface of a still body of water. Styrofoam is very not dense. Air is super not dense, so those things all float. But aluminum is, it's not a very dense metal, but it's more dense than water, so aluminum sinks. Then, number 7, adding thermal energy to an object. It's going to be a Q equals mc delta T situation. You add thermal energy and the temperature changes. We know the temperature change, we know the mass, we know that this object is made of water. Since we know what it's made of, we can look up the specific heat of water. You might notice this number has shown up a lot. It's because a lot of physics variables are based entirely around the behavior of water. So, specific heat of water, 4,186 joules per kilogram. We got mass of water, specific heat, change in temperature, always final minus initial. You can get away with using Celsius here because the delta T for Celsius is the same as the delta T for Kelvin. Still a difference of 100 units. So this is the thermal energy you would have to add to this amount of water to just increase its temperature. Brief concept question. Once you get water up to 100 Celsius, does it immediately all turn into steam? What do you have to keep doing to it to then cause it to evaporate?
Keep heating it?
Keep heating it. You have to keep giving it thermal energy. It'll stay at boiling until it's all evaporated, then it'll heat up again. So this is just to heat it up. This is not to actually turn it into steam. I also got some questions about number 8. It also involves Q equals mc delta T because various things are heating up and cooling down. But it might not be immediately obvious, but this one is also a Q lost equals Q gained situation because there are technically 2 objects involved, just 2 separate masses of water. They're both the same thing, but they're both undergoing different processes. You have the hot water cooling down and the cold water warming up. So there are 2 objects, each undergoing their own process. So one each belongs on one side of this interaction. The cold water will gain thermal energy, the hot water will lose thermal energy. So you plug in mc delta T on both sides and fill in the variables for each object separately, for each side separately. On the cold water side, you have 2 kilograms of water, and it goes from 45 degrees to some unknown final temperature. On the hot water cooling down side, you have this mass of water, heated water. It began at 100 Celsius, and it ends at some unknown final temperature. So what you're solving for here is the final temperature of both united bodies of water. It's going to be the same TF on both sides, so that's the variable you're looking for. This is the 1 TF on both ends. simplify it down to this line. You then want to rearrange to unite the two TFs. You'll eventually find out how much warmer the cold water got. Notice it's closer in temperature to the cold water because there was just more cold water. Oh, I didn't mention this. Density of water is 1,000 kilograms per meter cubed, but it's also, if you convert that, 1 kilogram per liter. So 2 liters of cold water has a mass of 2 kilograms. Next, number 9 is a thermal conductivity question, which means you want the thermal conductivity equation right here. We're taking refuge inside of a wooden shed. The fact that it's wood means turn to your notes, look up thermal conductivity table. Yeah, okay, there we go. Scroll over to non-metals. Where's my cursor? Non-metals, wood, 0.1. So written off to the side. Thermal conductivity of wood is 0.1. That's what's going to go in for K. A is the area of the walls, listed here. Temperature difference from hot to cold. Because it's hot minus cold, it's 25 minus negative 15. So a difference of 40. And then divided by the thickness of the walls, listed as 10 centimeters, but we need to convert all of our centimeters to meters. So this is our formula. This is what it looks like with everything plugged in. Eventually you'll solve for a thermal conductivity of 360 watts. Thermal conductivity, heat current, rate of thermal conduction, they're all synonyms. They all just refer to how fast thermal energy transfers through the object. So if it's written any of those ways, it is referring to this principle. And because a 1 watt is equal to 1 joule per second, if this is the rate of thermal energy leaving the cabin, you ideally would want some heater, like a fire or a furnace or just your regular electric heater. You would want something inside the building producing 360 joules of heat every single second to make up that difference. If you did not have something inside the cabin giving off this much heat every single moment, the cabin would eventually begin getting colder because you were losing thermal energy with time in this blizzard. So, again, electricians and then architects design their buildings to try to keep thermal energy from leaching through the walls, but then they install heaters and air conditioning to make up the difference from what is eventually going to leach through anyway. Yes?
What were those 3 terms that are that mean the same thing? Again,
Oh.
Rate of thermal energy.
Rate of thermal conductivity,
Thermal conductivity.
heat current, and thermal power. They all mean the same thing. All of those represent the P in this formula.
What was the second one?
Heat current. Current is defined as the rate at which something flows, so the rate at which heat flows.
And all those equal P.
Yes.
What was the third one?
Thermal power.
Yes. Thank you. Any questions about anything so far? Okay. 10 is a multi-parter that ties together several different concepts and formulas. So, gas burned in your car releases 1 million joules of energy, which is a lot. The engine does this by literally making it explode, and those explosions push out pistons, and that mechanical energy turns into wheel spin. From all of this gas burned, the engine only does 200 kilojoules worth of work. It's going to be 200,000 joules of work. Notice that is less than the energy you put in. So the first question is, what is the change in the engine's internal energy from this interaction? So internal energy, that's the energy that's going to remain inside of the engine. That's delta U. We know from from first law of thermodynamics, change in internal energy equals thermal energy in minus work done by the machine. So you put in 1 million joules worth of heat, it only does 200,000 joules of work. Therefore, the remaining difference of 800,000 joules of energy is just stuck inside the engine, not accomplishing anything. Then, part B asks, what is the efficiency of this engine? Efficiency, the nth value, is always work output divided by energy input. It's what you get out of the machine versus what you put into the machine. So this engine is about 20% efficient, which seems bad, but that's actually really good for a car, which means all automobiles waste energy horribly. Because combustion makes a whole lot of heat that you don't use afterwards. Oops. 20% efficient, and then part C, what is the change in entropy of this engine? Change in entropy is delta S, or one formula for that is just to look at how one object's entropy changes as the heat added to it changes. So delta S is delta Q over T. The object in, Okay, I could see you putting either the 800,000 or the 1 million in here, because the engine did gain that amount of energy either way. So I would also accept this as correct if you wrote 1 million up here. But at least if you plug in the 800,000, you do want to make sure your temperature is in Kelvin. If you plug in Celsius, your answer won't work right. What I have written here is 200 Celsius plus 273 in order to convert it to Kelvin. And then this would be the change in entropy. From that interaction, if you plugged in 1 million, it would be slightly higher, but I would also count it as correct. Just depends on your perspective. 3 different parts, 3 different concepts. Any issues here? Okay. Number 11 combines 2 different but similar pressure and flow formulas from chapter 6. So we have a water flowing through a hose, and the hose's cross-sectional area is going to change during that flow process. So that would look something like this. The hose just gets narrower towards the end, like most fire hoses or garden hoses tend to do. You have the actual width of the device, and then the nozzle at the end is narrower more often than not. So we do know the starting cross-sectional area, that is again just like the area of the circle that makes up the cylinder part. We know this area and this area, and we know the flow speed right here and the force driving the water forwards right here. From there we have 2 different formulas to figure out what the flow speed and the force here will be. So, to find flow speed, we have the continuity equation, A1 times V1 equals A2 times V2. In general, by making a hose narrower, the water will come out faster, which again is why you might put your finger over the end of the garden hose and the water shoots out faster. I do that when watering the grass because I don't want to walk all the way over there, so I'll just make the water come out faster. Different formula for the forces involved. Force 1 over area 1 equals force 2 over area 2. Volume gets bigger as area shrinks. Force gets smaller as area shrinks. But since there's more water coming out every single second, like if you were shooting a person with this, they probably feel ultimately the same amount of force. This is kind of like force per water droplet. And there's more water droplets coming out, it'll even out. But it gets faster because it's narrower. They all want to escape and they're pushing harder to get out, but the hose doesn't have to exert as much force to push them out. They're kind of just doing it at their own volition at this point. Then, number 12 involves first our basic pressure at depth formula from chapter 5, but also Bernoulli's equation from chapter 6. First thing we're asked is just what height of atmosphere above you would create standard air pressure. Standard air pressure, the air pressure acting on your body right now is 101,325 pascals. Your body is entirely used to this pressure, so you don't notice it. And that pressure is created from all of the air above us reaching into the atmosphere. So there must be some height of atmosphere above us creating that effect, which is what we're solving for here. Pressure at some depth in a fluid, P equals, sorry, this is big P for pressure, this is lowercase rho for fluid density, times 9.8 times height. So we know the pressure, I did write this a little out of order, sorry. This is the pressure, so P equals density times G times H. This is density times G times H equals pressure. It's air above us, so the density is air. G is 9.8 because we live on Earth, times some height of air above us equals this pressure, and you will get about 8,400 I. Now in reality, this might not match the exact height of Earth's atmosphere because the density of the air doesn't stay constant all the way up. But without knowing those density changes, this is a decent assumption for right now. Point is, it's a lot of air. You go up very high before you actually leave the atmosphere, and it's a gradual process of the air slowly getting thinner until you eventually hit the vacuum of space. But if Earth's atmosphere had a constant density, it'd be this high up. With that information, part B, the part involving Bernoulli's equation, at what height above the ground, at a high point above the ground, where the air pressure is half what it is down here, at what velocity does the air need to move in order to create the same total pressure? So this is only the pressure on Earth's surface because of all the air above us. The higher up you go, the more this drops because there's just less air above you. Which is why on top of mountains, the air pressure is less, water boils faster, and your ears start popping. And it gets harder to breathe. So, Bernoulli's equation is all about comparing the pressure in two different states, two different locations. First location we're going to consider to be the ground, and at the ground we have PGH, this much pressure above us from the air above us, but the air isn't moving, and there's nothing outside the air adding pressure, so these terms just go to zero. The trick with Bernoulli's is something is always going to be zero on one or both sides, so it simplifies very quickly. On the second side, we're looking at some point about half as high up. So for the PGH term, you plug in half as much height, because at that point up, there's half as much air above you. Now, at this height, the air, we want to know how fast the air needs to be to create the same effect as on the left. So the V term is no longer zero, plug in the density of air, solve for V2. There's still nothing outside the air creating this pressure, so this P term is still 0. When you solve for V, you find out that the air would have to be moving at about 300 meters per second to create the same effect. It doesn't happen, thankfully. And this is why, as you go up, regardless of wind speed, pressure will always drop. That is every practice question. I've been talking for a good long time, and I actually now need a break because I have to use the restroom. So I'm going to go do that. I'll get time to just grab some water, take a breather. If you have absolutely no review questions, you're under no obligation to stay. If you depart at this point, I do hope you all have a wonderful weekend. Please grab some candy on the way out. If you do stick around, more studying, more questions, I will be here until 4:30. And great on this test. It doesn't have as much stuff on it, just because the first test was just so many things. A little more focused this time. I've absolutely picked all of you. We're all leaving just fine. Please have some community. I don't want to have to do all this. It will be terrible for me. You guys do. Thank you. If I don't see you guys in person, have a good weekend. Please let me, again, send me word when you are taking the test and send me questions as you take it. And thank you all so much.
Thank you, President.